Hi everyone, this is just a quick little review of kinematics and dynamics. So for the next week we'll be doing short little reviews every day of different topics, getting ready for the AP Physics C Mechanics exam. So kinematics is how we describe motion, position, velocity, acceleration, all that stuff. Okay, and the idea is if you know enough of those quantities at one point in time, you can figure out what other ones will be later. So constant speed is one thing, but it's really too easy for AP Physics. So uniform acceleration is the most common thing that we deal with. So those are the equations that are given on your formula sheet. Oops, that should be a Q. So those are equations on the formula sheet. And there's really not much to say about those. You've used those pretty extensively, and this is one of those things on the AP test itself. You rarely have to go through complex calculations, and I would say that is even going to be less of a chance this year with the format of the exam. So one thing to remember, of course, is that you have projectile motion. So remember, in the horizontal direction you have constant speed, and in the vertical direction you have acceleration equal to, and I would use 10 meters per second squared. That's allowed on the AP exam. If you have to do a calculation, by all means use 10, make your life easy. But the relationships are important, so the graphs are going to be important. So I think interpreting graphs is something that is a common way for them to probe your understanding of the big picture relationships between these things. So remember, if you have position, and these are all versus time, so position versus time, I should have put that in there, velocity versus time, and acceleration versus time. Okay, and so remember that if you take a position versus time graph, the derivative is equal to velocity. So that is for velocity versus time, if you take the derivative, that is equal to the acceleration. And the acceleration versus time graph, if you take the derivative, it is something, but it's not something that we need to know. It's actually called jerk. If you want to know that, that's trivia. That's not going to be useful for you. If you win at Jeopardy with that, send me a cut of the money. Okay, now the other thing that we can do is we can look at area under the graph. Okay, well actually, so in terms of graph, remember a derivative is equal to the slope. So the slope of the graph, the slope of a position versus time graph tells you velocity. Slope of a velocity versus time graph equals acceleration. Or you may be given a function in terms of t, and you may use your calculus skills to find the derivative. Okay. The area of a graph, it definitely has meaning. So the area with a position versus time graph actually doesn't always have meaning physically, but area of a velocity versus time graph, remember, is equal to displacement. Okay, in other words, change in position, which we also call displacement. Okay, and so the acceleration, if you look at it, if you kind of are looking for a pattern here, so the acceleration graph, if we look at the area, the change in velocity is equal to the acceleration, the area on the acceleration graph. So we don't have a special name for change in velocity, but that is true. Okay, so on a graph we're talking about area. And so especially in this year's format, you're going to have to probably explain how you draw some conclusions, And so that explanation could be refer to the area of the graph or the slope on the graph or things like that that'll help you out in terms of creating an explanation that is concise and correct and easy to grade. So the other thing that we have to look at is dynamics, and dynamics is why do objects move the way they do, okay? And basically it comes down to Newton's laws. So remember, rest or constant velocity, Newton's first law says that F net must equal 0. So rest or constant velocity, F net must equal 0, and if something is accelerating, we know that F net is not equal to 0, and in fact F net is equal to the mass of the object times its acceleration. So that's Newton's second law. So those are, very general things. They're wonderfully useful, but the variety of situations they can be applied to are infinite. So that's what makes physics wonderful and challenging at the same time. So the universe is governed by a lot of fairly simple laws, but the universe is a complex place. So when it comes to doing these problems, using these, you want to have strategies. You want to draw a force diagram, okay? When it comes to force diagrams, you can label things in several different ways. You do not really need to use the on-by. We did the on-by for some things, okay? But you can label things as W and maybe N for a normal force and maybe T for a tension. Those all work. Or you can always use mg. That is always acceptable. Some people like the notation where they use F for force and they put the little subscripts for which type of force. You can do that. Okay, but like I said, it's not going to be necessary to use the on-by things, and honestly, not everybody who is looking at these or makes the rubrics is familiar with that, so you might actually be better off kind of leaving that by the wayside. Okay, so you can draw your force diagram. Remember that if you have a force that is at some sort of angle relative to the axes, so maybe we have F and mg and a tension or something like that. So that force F is not along the x and y axes, so then we want to think of components. Okay, but be careful, because often in the diagram, when they ask you to draw a force diagram, which I'm not sure there are going to be any drawings this year, but if they do ask you to make a drawing, remember they say don't put components on here, but we do want to think in terms of components. And then you use that to figure out relationships. So what do we mean by figure out relationships? So when we figure out the relationships, for example, if this object here that I'm talking about is at rest, for example, then what that means is the up and down forces have to balance out, the left and right forces have to balance out. So we could say that T is equal to Fx, and we could say that Fy is equal to mg. So that depends on the problem, and again, the state of motion. So let's do a few examples here. Okay, so the hanging sign. So that is something that is at rest, and this is similar to what I just did actually. So if this is our sign, it has a mass m. Let's call this 1 and this 2. So when we draw our force diagram, we're going to have a T2 there, we're going to have a weight force mg, and then we'll have a force T1, and then we're going to have some sort of angles there, but the T1 is going to have an x component, and a y component. I should put those dotted lines. Ty, okay, and then so the relationships, oh, we're nowhere at rest, so that means that the sum of the forces has to equal 0, or I like to say up and down forces have to equal 0, left and right have to equal each other, left and right forces have to equal each other. So again, you can come up with these relationships that Tx is equal to T2 and Ty is equal to mg. Okay. Let's think of another thing. So it used to be common for people to hang things from their rearview mirrors of their cars. Don't see it very much anymore. Some people had like a graduation tassel, things like that. But if you just had a small sphere, basically it acts as an accelerometer, something that tells you the magnitude and direction of your acceleration. But you generally don't want a small hard metal sphere, hanging from your rearview mirror. Especially the longer the string, the more dangerous it would be. But anyway, if the car is at rest, so if we draw a free body diagram or a force diagram for the ball, you would have a tension force and a weight force. I always just go ahead and write it as mg because they usually want things in terms of mass and constants, such as little g, rather than in terms of w. So it's at rest. So again, we could use equality marks there. So we've got T is equal to mg. Okay. But a case we may not have dealt with before, I can't remember if we have or not. If the car is accelerating forward, okay. So if you think about that, you're at a light, you slam on the gas, okay, floor it. If you think about that thing hanging from your rearview mirror, it would appear to be like going backward. Okay, so the idea is it has inertia. The windshield, the rearview mirror move forward, and then the ball has inertia, so it kind of like lags behind, if you want to think of it that way. And if we look at it in terms of forces, it's pretty clear what has to be going on now. Okay, so we've still got that mg force acting downward. Now we have a tension force at an angle. Okay, so we're going to think of those components, Tx and Ty. And if we look at this, we have two when it comes to the state of motion, actually, so that's going to be what I really wanted, was acceleration there. Okay, so this is the case in the vertical direction, there is no acceleration. So the acceleration is in the horizontal direction. So in the vertical direction, we know Ty is equal to mg. Okay. With a little knowledge of the angle there, you could then figure out what T is. But we know that in the horizontal direction, we know that it is accelerating. So we know that F net, hold on a second here. So we know that F net is equal to ma. So in this case, F net would be Tx. That x component, that would equal the mass times the acceleration. So that's a simple case, but you always want to rely on the strategy of looking at the problem. You want to draw a good force diagram, and then you want to look at the state of motion and allow that to determine what your equations are. So let's practice this a little bit. And so what I'm going to strongly suggest that you do, look at each of these problems. You might want to pause the video and look at one or both of these problems first before I go over these things. So I'll give you a chance to do that. Okay, so we want to rank the magnitudes of these forces from highest to lowest. I admit I gave this question to the AP Physics 1 class, and there were, some people did it very well. There were other common mistakes. Okay, but I would say if you draw the diagrams, everything's going to work out just right. Okay, so don't rely on sort of your intuition. Follow the strategy and draw your diagrams. So for that 10 kilogram box, okay, for that 10 kilogram box, you've got the weight force mg, and I'm just going to call that mg because the mass actually doesn't matter a whole lot. Okay, we've got the normal force, and we've got T pulling to the right, and there's also a frictional force, so that would be Ft. And then for the top, so that's the frictional force on the top surface there, and then on the 20 kilogram box, draw your diagram. You have mg, you have a normal force. So this one, if you think about it, so Newton's third law, there's a force on the top one by the bottom one to the right, so that means that there's actually Ft acting to the left on the bottom one, okay, and then Fb, so the frictional force on the bottom acting to the left there. Okay, so let's look at the state of motion of these things. So this one is accelerating to the right. This one is also accelerating to the right. Okay, so if we have acceleration, we have to have a net force. So right away you can compare T and Ft, and if it's accelerating to the right, we know that T has to be greater than Ft. Okay, and then if you look at the other one, it's accelerating to the right, so that means there has to be a net force in the rightward direction. So that means Ft has to be greater than Fb. So now it's pretty easy to put the ranking together. So if we rank the magnitudes, T has to be greater than Ft, which is greater than Fb. Okay, which in some ways is not intuitive. I think when I saw the student responses to this, you look at the masses, you might be tempted to think that Fb, because there's more mass, and the other one's on top, would have to be bigger. There are all sorts of different things that you can do that. So you have to rely on drawing the diagram, looking at the force, and then drawing your conclusions. That's the most reliable way to do things. Okay. Let's look at the next one, which is an Atwood's machine type of thing, which is a fairly common situation to see. If you haven't paused and gone over this already once, I would go ahead and do that now. Alright, so we look at this. So in case A, you're going to draw the diagram, okay, for that block, and you can see that we're going to have a normal force. We'll have a weight force, so you can call it mg, or you could even write the value. 10 times 10 would be 100 newtons. Okay, we've got a frictional force. Again, you could calculate the value that I'm not sure it's necessary here. And then we have a force, a tension force. I'm going to call that a tension force of 50 newtons. Okay. Now in case B, there's actually going to be two ways to look at it. So I'm going to do it as each box individually first. So there are two boxes. So again, I probably should have saved myself some time here. So we've got N, we've got 100, we've got a tension force, and we've got a frictional force. So the two frictions will definitely be the same as each other. I'm not convinced that the two T's will be the same yet. We've got to think through this. So that is one thing, and then we have the other object here. So that is going to be a, if we look at it, that's going to be an mg equal to 50 newtons. But there's also a tension force, and remember these two tensions are definitely equal to each other. Okay, so let's reason through this here. So the question is, in this case we know that the acceleration is basically based on this tension. So if we can compare this tension to this tension, and we'll kind of answer the question. So we know that that is 50. So if this is accelerating downward, okay, what do we know about t compared to 50? Does it have to be greater than, less than, or equal to 50? The 50 acting downward. Well, it can't be equal. If it was greater than, this would accelerate upward. That doesn't make any sense. So we know that t has to be less than 50, which also means that this t is less than 50. So if we look at the acceleration of this system, okay, the blocks are going to accelerate at the same rate. You can say for sure that that's less than 50, so this acceleration B is going to have to be less than the acceleration for case A. Okay. You could also look at this in terms of a systems approach. Okay, in case A, you know, the mass of the system is equal to 10 kilograms, okay, and the acceleration of the system is F net over m, so that's going to equal, if you look at F net over here, this is the system, it's going to be 50 minus F. Over 10. Okay. If we look at case B, so the system mass, if we consider the system to be the two blocks together, the system mass is equal to 15 kilograms. Okay. So the net force on the system, when you look at these two diagrams, okay, these two tension forces are internal forces, so we don't have to worry about that. So these two cancel out, so we don't have to worry about those. So the net force on the system is still the 50 Newton weight minus F, but now the system mass is 15 kilograms. So the acceleration is going to be less. So you can make a case both ways. So I really want to emphasize that. I think there's a lot of discussion amongst physics teachers about what you'll be asked to do, and I think it's going to be a lot of explanation and reasoning. You have to be able to type these things out and do things in words, and so you don't necessarily, it's not going to be as calculation based as previous years. Okay, so that wraps up this little kinematics and dynamics review.